Hello, welcome to my talk. This is the second part for the understanding of the Bernoulli's equation. Second example, Venturi Tube. Unlike the case of the tank outflow in the last example, where the energy conservation would be very similar to that of a free-falling body, the energy conservation is between the kinetic energy and the potential energy. In fact, Daniel Bernoulli tried to explain the phenomenon of the Bernoulli's principle using the energy conservation principle. And I would say that would work for his specific case. Here, the example is for the Venturi Tube. Venturi Tube is a short pipe with a narrow slot in the mid, here A2, generally in horizontal position, which was invented by the Italian physicist Giovanni Battista Venturi in 1797. He found, due to the change in the flow passage, the flow velocity and the pressure would be both changed, such that he could use the changes in the Venturi tube to measure the flow velocity and the flow rate. Here is a nice animation which I downloaded from the public domain. Thanks to the author for uploading such a nice animation. In this animation, we can see the fluid particles squeezed and stretched when they pass through the slot. However, this animation might not tell us how the principle is working for the flow past the slot. In the next two slides, we are trying to make the explanation to the flow phenomenon in the Venturi tube. In a direct tuition, we may imagine, due to the narrowing passage, we can see the streamlines are squeezed together in the slot. In this case, the fluid particles, see here, would be squeezed like this in the slot. In such a case, a higher pressure at the slot would be expected. Is this true? And in reality, we may experience the similar practical examples. For example, the people passing a narrowing tunnel. So we can see people may squeeze together at the narrowing passage in the tunnel. So slow down the flow of people. Another example, we might have the experience for the traffic. When the road is narrowed or a lane is shut down, the traffic will slow down. Are these phenomena similar to the flow past the narrowing passage in here? The second exploration would be a little bit counterintuitive. Due to the narrowed passage, the fluid particle would be squeezed in the perpendicular direction from here to here, following the streamlines. Meanwhile, the fluid particles would be also stretched in the fluid direction. So from this to this, such that the fluid would not be significantly compressed. As such, a higher velocity would be expected in the slot in the Venturi tube. The question may be how we can determine the velocity and the pressure. So, from these two explanations, we will ask which explanation is correct, or more relative to the talk, how we can solve the flow problem in the Venturi tube. This is a video of a Venturi tube experiment to show how the pressure is changed at the throat in the Venturi tube. Thanks to those who performed such an interesting experiment and uploaded the video for the public use. The Venturi tube is a short horizontal tube with a throat in the middle. A manometer of a U-shaped tube filled with the dyed liquid as the device to measure the difference of the pressure. The height difference of the dyed water would show the pressure difference. If there is no flow in the Venturi tube, we can see the dyed liquid is at the same level we can see here on both sides of the manometer. When the valve is open, we can see the dyed liquid would have different height on both sides of the manometer. And the higher position of dyed liquid means a lower pressure at the throat. And we can also see, regardless of the fluid direction in the Venturi tube, the pressure in the throat is lower, which is indicated by the higher position of the dyed liquid in the manometer. Next, we will examine the phenomenon using the Bernoulli's equation based on the conservation laws. That is, the mass conservation, which is based on the continuity equation, and the energy conservation, which is based on the Bernoulli's equation. Now we are going to solve the flow problem in the Venturi tube. Use a detailed example. In this example, we assume the air flow passing through the Venturi tube. The air density is taken by rho 1.25 kg per meter cubic. And the section 1 D1 at 0.15. So the section area is given by A1 here. And section 2 with a diameter of 0.075 meter, section area A2. Suppose we use a manometer, measure the pressure difference. The height is 0.2 meter. Here in the manometer, the dyed water is used. Its density, rho W, is 1000 kg per meter cubic. So in this plot, we can see high pressure in the manometer here and the low pressure here. So the difference between the high pressure and the low pressure make the different height of the dyed water showing as this. To solve the problem, we first use the continuity equation for a steady flow. So this would be given as A1 times V1 equaling to A2 times V2. So we have the expression for V2 at the throat given as this. For our example, since the diameter at the section 2 is only half of the diameter at section 1, So the area A1 would be 4 times the area of A2. This means the velocity V2 would be 4 times of the velocity at A1. Now we apply the Bernoulli's equation for A1 and A2. So we have the expression as this. Why we have the Bernoulli's equation as this for the fluid in the tube, rather than building the Bernoulli's equation on the individual streamlines. The reason for this is because for the pipe flow, the velocity and the pressure would be both uniform on the sections, while compared to the time and the pressure, this time change in the pipe would be very small, even from the bottom to the top of the pipe. That's why we can employ this equation for the whole flow in the Venturi tube. Now we consider the height Z1 at the section 1 and Z2 at section 2 are same on the center line of the Venturi tube. So we can cancel out these two terms, and we can calculate the pressure difference delta P given by P1 here minus P2 at the throat given by the velocity V2 and V1. So we have the expression as this. And from this equation, we can easily calculate the velocity V1 given as this, if the pressure difference can be measured. For the manometer, the pressure difference can be calculated given as this. Note here, rho W is the density of the liquid in the manometer, so H is the liquid height difference. So if we use this expression, we can obtain the velocity V1, and from that we can calculate the flow rate Q and the velocity at the throat V2 given by all these formulas. Now we look at all these parameters. A1, A2 are the section areas at here and the throat. So this can be determined when the Venturi tube is made. And the density rho and rho W can be calculated from the media used for the experiment. And if the temperature is very different from the conventional indoor temperature, we might need to collect the density. And H can be measured in the experiment. G is the given constant, the gravitational acceleration, 9.81 meter per second squared. So here, for this example, we can calculate the pressure difference by the measurement H, as we shown before, 20 centimeter. So the pressure would be 1,962 pascals. And V1 can be calculated using this expression. So the velocity at the large diameter would be 14.47 meters per second. V2 given by this 4 times of V1, so it is 57.87 meters per second. And the flow rate calculated by this A1 times V1, it is 0.256 cubic meters per second. So we can see, using the Venturi tube, we can easily calculate the flow speed and the flow rate by measuring only the pressure difference. And this principle can be also used for measuring the airspeed of the wind tunnel, where the large tube can be taken as the settling chamber, and the narrow throat is the working section. So by similar principle, measuring the pressure difference, use the manometer, the airspeed in the wind tunnel can be calculated in the same calculation. Here, some few words would be made. Physical laws would be vitally important for solving the practical problems. These laws including mass conservation, via the continuity equation, the moment conservation via the Newton's second law of motion, and the energy conservation via the Bernoulli's equation for mechanical energy conversions, or other forms of energy conservation. So these are very important even for those phenomena which might be counterintuitive, but the laws must be satisfied for all practical problems.